Assalamu alaikum. My name is Filzatif and my group member is Sundas. Today our topic is altering an equilibrium mixture pressure, volume and temperature. So by starting changes in pressure and volume, to illustrate how an equilibrium mixture is affected by a change in pressure as a result of a change in the volume, let's return to the Haber synthesis of ammonia. The balanced equation of the reaction has 4 moles of gas on the reactant side of the equation and 2 moles on the product side. And here is the example. And the equilibrium constant is 0.291 at 700 Kelvin. So here is the question. What happens to the composition of the equilibrium mixture if we increase the pressure by decreasing the volume? So the pressure of an ideal gas is inversely proportional to the volume. At constant temperature and constant number of moles of gas, which is pressure is equal to amount of substance, ideal gas constant, temperature over volume. So before going forward, we have to remember what is Le Chatelier's principle. So when a system at equilibrium is stressed, the system works to store equilibrium. So net reaction will occur in the direction that relieves the stress of the increased pressure, which means that the number of moles of gas must decrease. Therefore, we predict that the net reaction will proceed by left to right because the forward reaction converts 4 moles of gas reactants to 2 moles of gaseous products. In general, Le Chatelier's principle predicts that an increasing pressure by reducing the volume will bring about net reaction in the direction that decreases the number of moles of gases. A decreasing pressure by expanding the volume will bring about net reaction in the direction that increases the number of moles of gas. So equilibrium will shift to the side of other reactions with fewer moles. Let's look again at the reaction quotient of the equilibrium mixture of 0.50 mole of N2, 3 moles of hydrogen and 1.98 mole of ammonia at 700 Kelvin. So as we all know that number of moles converted into the power. So by applying the power, the equilibrium constant becomes 0.29. If we disturb the equilibrium by reducing the volume by the factor of 2, we not only double the total pressure, we also double the partial pressure and thus the mole concentration of each reaction and product. Because a balanced equation has more moles of gaseous reactants than gaseous products, the increase in the denominator of the equilibrium constant expression is greater than the increase in the numerator, and the new value of quotient is lesser than the equilibrium constant Kc. So here is an example. For the system to move to a new state of equilibrium, reaction quotient must increase by means that the net reaction must go from reactant to product as predicted by Le Chatelier's principle. A mixture of gaseous N2 and H2 and NH3 at equilibrium is equal, but when the pressure is increased by decreasing the volume, the mixture is no longer at the equilibrium. So net reaction occurs from reactants to products, decreasing the total number of gaseous molecules until equilibrium is re-established. In practice, the yield of ammonia in the Haber process is increased by running the reaction at high pressure, typically 130 to 300 atm. The composition of an equilibrium mixture is unaffected by a change in pressure if the reactant involves no change in the number of moles of gas. For example, the reactant of hydrogen and gaseous iodine has 2 moles of gas on both sides of the balanced equation. Hydrogen and iodine become hydrogen iodide. If we double the pressure by halving the volume, the numerator and denominator of the reaction quotient changes by the same factor and reaction constant remain unchanged. In applying Le Chatelier's principle to a heterogeneous equilibrium, the effect of the pressure change on a solid and a liquid can be ignored because the volume and the concentration of a solid or a liquid is nearly independent of pressure. Consider, for example, the high temperature reaction of carbon with steam. The first step in the conversion coal to gaseous fuel is this. Ignoring the carbon because it's a solid, we predict that a decrease in volume, increase in pressure will shift the equilibrium from product to reactants because the reserve reaction decrease the amount of gas from 2 moles to 1 mole. We have been careful to limit the application of Le Chatelier's principle to pressure change that results from the change in volume. What happened through if we keep the volume constant but increase the total pressure by adding a gas that is not involved in the reaction, say an intern gas such as argon. In that case, the equilibrium remains undisturbed because adding an inert gas at constant volume does not change the partial pressure of the molar concentration of the substances involved in the reaction. Only if the added gas is reactant or product does reaction quotient change. That's all from my side.
Assalamu alaikum. My name is Sundar Salil and I am telling you about the altering and equilibrium mixture changes in temperature. When an equilibrium is disturbed by a change in concentration, pressure, or volume, the composition of the equilibrium mixture changes because of reaction quotient no longer equal the equilibrium constant. As long as the temperature remain constant, however, concentration, pressure, or volume changes don't change the value of the equilibrium constant. By contrast, a change in temperature nearly always changes the value of the equilibrium constant. For the Haber synthesis of ammonia, which is an exothermic reaction, the equilibrium constant decreases by a factor of 10 over 11 over the temperature range 300 to 1000 K. Here are the diagram. At low temperature, the equilibrium mixture is rich in NH3 because equilibrium constant is large. At high temperature, the equilibrium shifts in the direction of nitrogen and hydrogen. In general, the temperature depends of an equilibrium constant depends on the sign of delta H for the reaction. The equilibrium constant for an exothermic reaction, negative delta H, decreases as the temperature increases. The equilibrium constant for an endothermic reaction, positive delta H, increases as the temperature increases. You can predict the way in which equilibrium constant depends on temperature by using Le-Charles principle. If a reaction is endothermic, add heat to the reactant side of the equation. If a reaction is exothermic, add heat to the product side of the reaction. Take the endothermic decomposition of N2O4 for example. Here are the equation chemical. Le-Charles principle says that if heat is added to an equilibrium mixture, thus increasing its temperature, net reaction occur in the direction that relieves the stress of the added heat. For an endothermic reaction such as the decomposition of N2O4, heat is absorbed by reaction in the forward direction. The equilibrium therefore shifts to the product side at the high temperature, which means that equilibrium constant increases with increases temperature because N2O4 is colorless and NO2 has a brown color. The effect of temperature on the N2O4 minus NO2 equilibrium is readily apparent from the color of the mixture. For an exothermic reaction such as the Haber synthesis of NH3, heat is absorbed by net reaction in the reverse direction. So equilibrium constant decreases with increases temperature. Here are the chemical equation. That's all from my side. Thank you.